Hello everyone, welcome to lecture 54 of the course Diffusion in Solids. Last lecture we started talking about the diffusion in semiconductors, and semiconductors are one of the most important class of materials, particularly nowadays with technology surrounding us in every sphere of life. And what we saw is that a couple of key aspects that due to the covalent bonding in semiconductors, the defect formation energies are extremely high, and therefore the concentration of the defects is very low, and therefore usually we saw the example of self diffusion in germanium, self diffusion in silicon. This diffusion is lower than that of metals, which are more close packed structure. Another thing that we also saw is that because of the open structure of the semiconductors such as silicon and germanium, they crystallize in diamond cubic structure. So, this open structure allows the interstitials, the self interstitials also to have a comparable concentration with vacancies, whereas in metals we have seen that vacancies are the more dominant point defects. So, today what we will see is the diffusion of foreign atoms in semiconductors and some of the key features associated with that. So, the foreign atom in silicon, the primary dopants are the group 3 elements, for example, boron, aluminum, gallium, and group 5 elements which are phosphorus, arsenic and antimony. So, these are the key dopants which gives rise to p-type semiconductors and n-type semiconductors. They have a fairly high solubility, almost next to the group 4 elements. Now, dopant diffusion we all know is critical, and it is critical to create p-n junctions of the microelectronic devices. So, how much a dopant diffuses is very important to understand to create several devices, because remember, sometimes you want the diffusion to occur, sometimes you do not want the diffusion to occur. In any case, you need to be aware of the diffusion behavior of these foreign atoms into your semiconducting material. Incorporation of impurities such as iron, nickel and copper during thermal treatments of device fabrication. So, depending on how fast they go into your material, the control of impurities become that much more difficult. For example, oxygen diffusion and growth of SiO2 precipitates, they play a crucial role in getting process of unwanted foreign elements. So, silicon is very prone to the oxidation. Then diffusion behavior of foreign elements is largely determined by the type of solution, that is whether they are located at the substitutional sites or interstitial sites or a mixture of both. A few words about the solubility. So, typically in let us say silicon and germanium, if you try to see the phase diagram, it is not for every element, but a typical foreign atom semiconductor phase diagram looks like this, where on the dopant side, we rarely go to this area, but you see a normal solubility curve. On the semiconductor side, that is silicon, germanium and so on, what you see is something known as the retrograde solubility. What is this retrograde solubility? So, as I said that first of all, the solubility of a foreign element is the maximum concentration which can be incorporated without forming a new phase. Okay. So, as long as you can incorporate without forming a new phase, that is the maximum limit is what is known as the solubility. And usually the solubility, you can see it increases as you increase the temperature. So, solubility follows typically an Arrhenius type of behavior. So, this basically implies that the maximum solubility is achieved at a temperature which lies below the melting point of the host crystal and above the eutectic temperature. So, below this maximum temperature, the solubility can often but not always be approximated by an Arrhenius relation. So, you see the two types of solubility behavior here. Here, this is a more conventional type of a solvus line, where the solubility increases with increasing temperature and beyond. So, solubility is maximum at the eutectic line. However, on the semiconductor side, what you see is that solubility is not maximum on the eutectic line, but it is maximum somewhere here, which is a temperature which is below the melting point of the semiconductor, but above the eutectic temperature. Such a solubility is known as such a solubility behavior is known as the retrograde solubility. So, you understand the difference clearly here. If you see, the solubility is maximum at the eutectic line, at the eutectic temperature, whereas in the case of retrograde solubility, then the temperature, the solubility which is maximum is not at the eutectic temperature, but somewhere in between the melting point of the semiconductor and the eutectic temperature. Now, depending on the foreign element, the solubility can vary over orders of magnitude. For example, boron, phosphorus, arsenic in silicon, and aluminum, gallium, tin in germanium can be incorporated to several percentage into the host crystals. Whereas some of the other dopant elements such as gallium, antimony, lithium in silicon, and arsenic and antimony in germanium have maximum solubilities only in the range of 10 power minus 3 atomic fractions. Noble metal impurities such as iron group impurities, nickel group impurities, cobalt group impurities, and zinc, they have very low solubilities in the range of 10 power minus 6 atomic fractions. So, these basically the transition metal groups have extremely low solubilities in the semiconductors, which are in the range of 10 power minus 6 atomic fractions. Now, every foreign atom may occupy both substitutional and interstitial sites in the lattice. So, suppose if a foreign atom A comes, it may occupy a substitutional site and you call it as AS, and or it can occupy interstitial AI sites in the lattice. And remember, this is more common in semiconductors than in metals because of the relatively open structure of the semiconductors. The equilibrium solubility of either configuration, whether it is CS or CI, is determined by the corresponding enthalpy and entropy of the solution. Now, for most of the foreign atoms, one of these configurations, either the substitutional or the interstitial, is dominant in the temperature interval where you typically study the diffusion, which is 0.6 to 0.9 Tm. Now, the dopants which are dissolved in the substitutional sites, they diffuse with the aid of intrinsic point defects. So, the ones which occupy the substitutional site, they move with the help of intrinsic point defects. Foreign atoms with higher concentration in interstitial site, that is CI equilibrium is much greater than CS equilibrium, they diffuse via direct interstitial mechanism. So, this is intuitive that if the foreign atoms predominantly occupy the interstitial sites, then they would tend to diffuse by the direct interstitial mechanism. For example, the group 1 and group 8 elements. The foreign atoms where CI equilibrium is much less than CS equilibrium, that means the foreign atoms which predominantly occupy the substitutional sites, but they still have a minor interstitial fraction, they diffuse by interstitial substitutional mechanism. An example of this is noble metals. So, you see, we saw last time also that it is not just the concentration that matters, but also the diffusivities which will come into picture. And interstitial, usually the diffusion is faster. So even if the concentration is much lower, but if you still have a minor interstitial fraction, then usually you tend to get a combined interstitial substitutional mechanism. The equilibrium concentration on substitutional site CS equilibrium and equilibrium concentration on interstitial site CI equilibrium, they depend upon solute, solvent and temperature. They can have dissimilar variation with temperature. So, for example, this is also quite commonly observed that if the solute equilibrium concentration on substitutional site is increasing with temperature, the concentration in the interstitial site may decrease with temperature. So, they can have the dissimilar variation with temperature. Now, the ratio of this CI equilibrium by CS equilibrium may change with the background doping because of the different electronic structures of AS and AI. So, as you increase the doping, it may change this ratio, because the moment you increase the doping, we saw that the energy levels get changed, the local electronic structure get changed. So, and interstitial and substitutional sites have a different surroundings. So, the background doping can affect this ratio. For example, cobalt in intrinsic silicon occupies primarily the interstitial site, COI is donor, whereas copper in cobalt in phosphorus doped silicon, that means now the doping has been done, it acts like it is acceptor like cobalt substitutional sites are abundant. So, the same element same element in the same semiconductor, but one case you have intrinsic semiconductor, another case you have a doped semiconductor. So, the ratio of interstitial to substitutional sites can change. In intrinsic case, cobalt occupies predominantly interstitial sites, whereas in the phosphorus doped silicon, it occupies the substitutional site. Now, let us talk about the interstitial diffusion of foreign atoms. So, the diffusion coefficients are fairly high, commonly in the range between 10 power minus 7 to 10 power minus 10 meter square per second near the melting temperature. The decrease of the diffusivity with decreasing temperature is moderate due to relatively small activation enthalpies between 0.5 to 1.5 eV. So, this is in line with the interstitial diffusion mechanisms. So, typical examples are hydrogen or lithium in germanium, or hydrogen, lithium, copper, nickel and iron in silicon. Usually, the interstitial foreign atoms show donor character. This relates to the tendency not to interact with the host atoms by adopting the smallest possible closed electron shell configuration. Now, since intrinsic points defects are not involved in the interstitial diffusion, there is no connection with the self diffusion of the semiconductor host. So, one of the most important interstitial elements for the semiconductors are the hydrogen and oxygen. They are the most important solutes in the silicon technology. In the Czochralski silicon process or in the silicon produced by Czochralski technique, oxygen is incorporated during the growth process from the quartz crucible in some concentrations. Since in most silicon crystals the grown in oxygen concentration exceeds the oxygen solubility at lower temperatures, SiO2 precipitates formed by post growth diffusion process. So, oxygen solubility at lower temperature is low. Whereas the contamination that comes from these processes exceeds that solubility, and therefore, you have a ready formation of SiO2 precipitates during the post growth diffusional process. So, these precipitates act as sinks for unintentionally introduced fast diffusion diffusing metallic contaminants that must be included from the active regions. This process is called intrinsic gettering. So, this SiO2, although they are not the desirable ones, okay, but these acts as a sink for the unwanted metallic contaminants which are fast diffusing. So, in a way, although you did not want ideally the SiO2, but these SiO2 also have a beneficial effect. So, oxygen diffusion in silicon is written as given by this expression with the activation energy of 2.53 electron volt, and here this is the pre-exponential factor. So, the activation enthalpy for oxygen diffusion is higher compared to hydrogen and to the metallic diffuser. This is explained here. This is because of the steric hindrance that is involved in oxygen migration. Now, let us talk about the dopant diffusion in germanium. So, dopant and self-diffusion in germanium are consistently explained in terms of vacancy mechanism. So, we saw in the previous lecture the self-diffusion in germanium also predominantly happens by the vacancy mechanism. Diffusion of group 3 elements is slower, boron or slower or similar. Similar is gallium to self-diffusion of germanium. By contrast, the diffusivities of group 5 elements, phosphorus and arsenic, are 1 to 2 order of magnitudes larger than the self-diffusion coefficient. So, in the case of germanium, the group 3 elements diffuse slower than germanium self-diffusion, whereas the group 5 elements diffuse faster than the germanium self-diffusion. So, this is consistent with the fact that self-diffusion in germanium occurs by a vacancy mechanism with contributions mainly from neutral and negatively charged vacancies. So, negatively charged vacancies are present, therefore, you will see that the n-type doping elements they tend to increase the diffusion coefficients. An ionized donor atom carries a positive charge. Coulomb attraction enhances the probability to find a negatively charged vacancy in the neighborhood of a donor atom. So, because the donor atom which is ionized, it carries a positive charge. So, it has enhanced probability of finding a negatively charged vacancy, and since germanium has negatively charged vacancies, so you get higher diffusion rates for the n-type dopants. About the dopant diffusion in silicon, contrary to the case of germanium, the diffusion of common dopants, boron, phosphorus, arsenic, antimony, so that means group 3 as well as group 5 in silicon is always faster than the self-diffusion, irrespective of whether the atom has a smaller or a larger size than silicon. So, all the type of dopants usually have a faster diffusivity than the self-diffusion of silicon. So, this suggests that the diffusion of dopants is mediated by vacancies and self-interstitials both. Now, the diffusion of dopants can be represented as As plus V. So, this is the reaction of substitutional plus vacancy, which gives rise to AV complex. So, this V can be charged vacancies or the neutral vacancies. Similarly, the AI plus I is AI. So, I is can be charged vacancy or the charged self-interstitials or neutral self-interstitials. So, the total diffusivity is diffusivity of each of these complexes, dA AV plus dA AI plus AV plus AI plus and so on. Coulombic interactions between positively charged donors or negatively charged acceptors and the charge defect configurations provide a contribution to the defect dopant interaction. So, these complexes, if they carry charge, and then how they react or how they interact with the charge defect configurations, they also have an influence on diffusion. In this, every single term is a product which contains a geometric factor, parameters squared, the equilibrium concentration of the defect, a Boltzmann factor with the nearest neighbor interaction energy of the dopant defect pair, and a correlation factor. So here each of the D is typically has the factors that we already saw. As a G, you have the lattice parameter squared, the defect concentration, Boltzmann factor, and so on. So this particular figure, it illustrates the vacancy enthalpy varies as a function of the coordination site relative to the distance from the substitutional dopant. Okay, so depending upon where this complex is, how far it is from the dopant, the energies will vary. So here you see that HVM, it is the migration enthalpy of an unperturbed vacancy. So for example, if this vacancy is an unperturbed vacancy because it is far away, so this is the delta H HVM. HAVM is the activation enthalpy for the vacancy dopant exchange jump. So if there is a vacancy here, what is the enthalpy for vacancy to exchange position with the dopant? HAVB is the total binding enthalpy of the vacancy dopant pair. How much is the binding enthalpy? And then HAVB3 is the binding enthalpy when vacancy and dopant atom are separated to the third coordination shell. Now, for a long range migration, an AV pair must partially dissociate. So, this should dissociate to at least third nearest neighbor sites and return to the foreign atom via a different path to complete a diffusion step. So, the total delta H is a combination of these HVF minus HAVB plus HAVM plus CAV. Here CAV comes from the temperature dependence of the correlation factor. So, this is written as minus Kb dou ln FAV by dou 1 by T. And the activation enthalpy of vacancy mediated self diffusion delta HV minus delta HAV can be written as like this. So, the activation enthalpy of self diffusion is larger than that of the dopant diffusion by the same mechanism. The hybrid solutes like gold, platinum and zinc in silicon and copper in germanium diffuse via interstitial substitutional exchange mechanisms. The diffusivities of hybrid elements in silicon and germanium are higher than the self-diffusivities of silicon and germanium. A comparable fraction of foreign atoms resides in the interstitial sites, and the migration enthalpies of those atomic jumps are small due to weak coupling to the host lattice. So, as I said that hybrid solutes, because they have a certain fraction in the interstitial sites, and interstitial sites the diffusion is always faster, because you always have the probability to find a neighboring atom for exchange. So, you have the interstitial diffusion which occurs faster, and hence the hybrid solute tend to diffuse faster than the self diffusion in silicon and germanium. So, the defect control diffusion of hybrid solutes, so the effective diffusivity when both interstitial, self interstitials and vacancies are involved is given as Ci equilibrium di by Cs equilibrium into Ci equilibrium by Csx whole square plus Cv equilibrium by Cs equilibrium into dV. So, this is Cs of x. So, because the effective diffusivity depends upon the actual concentration, so the normal Fickian analysis cannot be used. Remember that when we talked about diffusion couple, because the concentration dependent diffusivity is present, so you cannot take the diffusion coefficient out of the Fick's second law partial derivative, and hence the analysis becomes complicated. So, this is expected for crystals with low densities of dislocations and other extended defects. which act as internal sources and sinks for intrinsic defects. And then you have interstitial controlled diffusion of hybrid solutes. If enough sources and sinks are present, then the thermal equilibrium of self interstitials and vacancies can be maintained during diffusion. And in such a case, then effective DI is written as CI equilibrium into DI divided by CI equilibrium plus CS equilibrium. If you take CS equilibrium out, since then the 1 plus CI equilibrium by CS equilibrium is almost equal to can be neglected or it can be neglected, then it becomes, the equation becomes CI equilibrium divided by CS equilibrium into DI. So, the DI effective, you see here there is no actual concentration coming into picture. These are, remember, these are the equilibrium concentration, whereas in the previous expression you had the CSX, which is the actual concentration. So, in this case it is independent of the actual concentration, and hence the normal Fickian analysis can be performed. So, hybrid atoms, we saw when we talked about the mechanisms, there are two mechanisms. One is dissociative, another is kick out mechanism. So, copper, silver, gold in germanium, they tend to follow the dissociative mechanism, whereas gold, platinum, zinc and sulfur in silicon, they diffuse by kick out mechanism. For copper in germanium, this product CI equilibrium into DI of copper is very large than the vacancy product, corresponding vacancy product for germanium, and therefore the diffusion behavior is dependent on the dislocation densities. For example, or in the case of silver and gold in germanium, this product CI equilibrium into DI AG is much less than CV equilibrium into DV equilibrium for germanium, and similarly for gold also. So, here the penetration and shape of the diffusion profile is independent of the dislocation densities. Okay. So, because the difference comes because the dislocation acts as a sources or sink for the defects like vacancies. So, when this concentration is very low, then the diffusion behavior is influenced by the dislocation densities. But when this product is already large, then the shape of the diffusion profile and the penetration is independent of the dislocation density. So, with this we will end today's lecture, and we will continue the next video. Thank you.